Okay, so 3.2 is polynomial functions and their graphs. So what we were graphing before were quadratic functions or parabolas, which those are actually polynomials too. But basically, we're going to look at higher ordered polynomials, so higher powers. And the higher the power goes, the more possible twists and turns we're going to have on our graph, and the more possible x-intercepts we are going to have. So here's some kind of examples of some of the stuff we are going to graph. They're going to look kind of similar to what we're looking at here. Here are some examples uh, of graphs that are not, these are not polynomial functions because they might be disconnected or they might have a sharp corner or something like that. But yeah, ours, for the most part, what we're going to be graphing should look pretty much like what you're seeing here. There'll be different variations, but it'll be kind of similar to that. And so before we can just jump in and start graphing them, though, we kind of have to learn about some of their behaviors and stuff. And so one of the big things that we're going to learn is this thing called end behavior. And so what happens is typically these graphs are going to have some twists and turns in the middle. Well, what's going to happen is the end behavior as x goes to positive infinity, either the graph has to go up or down on these polynomials. They either go up indefinitely or they go down indefinitely. And so in this particular example, as x goes to positive infinity, the y value also goes to positive infinity. And then over here, as x goes to negative infinity, the y value actually goes to negative infinity also, right? It's going down. So as x decreases indefinitely, the y value will do the same behavior right here. But that's not always the case. If you look at this second picture right here, as x goes to positive infinity, so does the y value. The y value increases indefinitely also. But over here, as x goes to negative infinity, y actually goes up to positive infinity over here. So that's kind of the end behavior. And then we'll learn, we already know about how to find the x-intercepts, and so that'll be another thing that we'll kind of review, and there's a little added detail to that. But those are going to be kind of the key things that you have to do in order to graph these. So you got to figure out the end behaviors, find the x-intercepts, and then typically you find a couple extra points to kind of figure out what's going on between your x-intercepts. And so really, I just kind of gave you the whole gist of it, but we'll start with in behavior. It's also, there's this thing called the leading coefficient test, and that helps us determine those behaviors. So the behavior of the graph of a function can be determined by the degree of the polynomial and the sign of the leading coefficient, okay? And so I want to pull this up to where we can see the examples down below. And so the leading coefficient is always going to be the value right here. The leading term right there is going to be the one with the highest power. It's going to be the term with the highest power. And so it's kind of in control because whenever you plug numbers in, that's going to be the biggest number that comes back because it's got the highest power, right? And so if I plug in, 10 or negative 10, sure, you get some other values here behind it, but this one's always going to be the one that's kind of the biggest value that is returned. So it's kind of in control. So if the leading coefficient is positive, so that's the value in front, which this one's positive, but this one is negative over here on my second example. If it's positive, the right end of the graph, basically as x goes to positive infinity, as x grows, as you let your x value just continue to get larger, 1, 2, 3, 4, 5, and so on, what happens? Well, it will rise. The y value also will go to positive infinity. So if the leading term is positive, the right end will go up. The right end will go up. Now, if the leading coefficient is negative, then the right end will actually go down. It will fall. And so you can see that here on the second graph that it falls down. And so really, if you just kind of take a moment to think about it, it kind of makes sense because as x goes to positive infinity, you're plugging in bigger and bigger values like 5, 6, 7, 8, 9, 10. Once again, these values over here, yes, they do play a role, but in the end behavior, they get overshadowed by the leading term because it's got the highest power, and so it's going to be much larger than all those other terms behind it, okay? And so think about this. If I plug in a positive number and raise it to a power of 3, I'm going to get a positive number in return. Even if some of these back here are negative, it doesn't matter. That leading term is going to overtake it. Now, on my other example over here, I plug in a positive number, and yes, I will get a positive number in return, but the problem is I've got that negative waiting for me right there, and it's going to turn my result negative. So I plug in a big positive number, I get a big positive number back, but then it changes to a negative because of the negative sign that's in front right there. Once again, these guys play a role, but they're going to be smaller than my value here in front. This value here in front is going to overtake anything else that may happen in the in the function right here. So, you know, simply put, if the leading coefficient is positive, the right end is going to go up. If it's negative, the right end's going to go down. That's kind of the easy way to think about it, but I kind of like to take a little deeper dive, because if you kind of understand why that occurs, then you don't really have to memorize it. You just kind of understand, oh, well, yeah, if I plug in a positive number, I get a positive number back. If I plug in a positive number here, it will come back negative because of that negative value, that negative sign that's in front. Because just to kind of clarify this, what's going on here is that negative, it's like having -1 times x to the power of 4. So you do the power first, and then the negative gets applied to it, and that's why when you plug in a positive number, you actually get a negative value in return. Okay, now let's talk about the left end behavior. Now that is dependent upon the degree of the polynomial. The degree of the polynomial, the exponent, what is it? If it's even, then the left end behavior is going to have the same behavior. So the left end behavior as x goes to -infinity will have the same behavior as the right end. So if it's an even power, like on this example right here, you have a power of 4 as the leading coefficient term. The leading term is an even power, so the left end behavior is the same. It's even Steven. But also, if you think about it, if you plug in negative numbers, a negative number raised to an even power will actually come back as a positive number. And so that's what's happening here. So even if you plug in like -10, -11, -12, when you raise it to an even power, it's going to come back positive. And then wait a second, you've got that -1 in front in this particular case. In this particular case, you have that -1 in front that makes it to where the y value is falling, or it's going down. It's going to -infinity. Once again, the simple rule is if it's even, it's going to be the same. So if you have an even power, it will be the same as whatever the right end behavior was. So even Steven. If it's odd, then the left end behavior will be the opposite. The left end behavior will be the opposite. So if you look at the first example, you can see that I had an odd power here. And so I actually went in the opposite. And so, oops. Let's see. So, okay, sorry about that. So what we can see here is if I plug in like some negative values like -4, -5, and so on, a negative number raised to an odd power will actually stay a negative number. It will actually stay negative, right? So a negative times a negative times a negative will result in a negative value. So yeah, if I plug in negative values, it will actually come back negative if it's odd, right? So let me just kind of recap this, and the thing is, once we apply this a couple times, you'll find it fairly simple. But at first it can be a little bit kind of confusing. But just kind of review: if the leading coefficient is positive, the right end goes up. If the leading coefficient is negative, then the right end goes down. If it's an even power, then the left end will be the same. So if it's an even power, the left end will be the same behavior. And then if it's an odd power, then the left end behavior is going to be the opposite. Okay, so you can follow the leading coefficient rule if you want. It's fairly simple to follow. Or just kind of think about it. Like if I plug in a positive number to the first value, will it come back positive? If I plug in a negative value, will it come back positive or negative, right? And it can be that simple also. And so let's try a couple of these. So right here it says use the leading coefficient test to determine the end behavior of the graph of the polynomial function. So right here we want to look, okay, so as x goes to infinity, basically as x goes to the right, that's what that means basically. As x goes to infinity, what's going to happen? Well, it's a negative value in front, so that means that the y value is going to come back as a negative value. So that's going to go to negative infinity. So if I'm following the leading coefficient test, it basically says my right end behavior is dependent upon the sign. It's dependent upon the sign of this. So if it's negative, it's negative. If it's positive, it's positive. But if you just kind of think about it, once again, you can just kind of ignore that stuff for right now. You're really just focused on this first term. Um, think about it. If you plug in 5, 6, 7, 8, 9, 10, those numbers, it's going to come back as negative numbers because that negative is getting applied after I do the power of 3. So I plug in a number, I get my number, but then it turns negative because of that. And so that's what's happening here. Now, for the left end behavior, as x goes to negative infinity, this would be the left end behavior. You're supposed, if you're following the leading coefficient test, you focus on the power right there. If the power's odd, it's going to be the opposite, right? Odd, opposite. So I'm going to do the opposite. I'm not going to go to negative. I'm actually going to go to positive infinity. Now, once again, you can kind of just think about this. If you were to plug in a negative number and raise it to a power of 3, what's going to happen is that negative number will stay negative, but then it gets multiplied by the negative that's on the outside, and so it actually turns positive, right? So if I were to plug in a negative number for x, if I were to put a negative number there, raise it to a power of 3, I get some negative number in return, right? Then that negative gets multiplied by the negative out front, which then in turn turned into a positive. Now, the reality is what's happening is there's some ups and downs in the middle, and what we know is that to the right, it's going to eventually go down, right? And we know that eventually to the left, it's going to go up. And so what we're going to look at after we practice this a little bit more is we're going to try to figure out what is that happens in the middle. So right now, we're only really kind of focused on what's happening on my extremes, what's happening all the way to my right, what's happening all the way to the left. We haven't really talked about the middle part yet, and that's okay. That's, we're just taking it a piece at a time, and then eventually we're going to put it all together. Okay, let's look at example B. So once again, you just need to focus in on this. You don't really, need to worry about that right now. Yes, that's very important. That has more of an effect on the middle part of the graph, and we'll worry about that in a little bit. One thing at a time. All right, so first, as x goes to infinity, basically as x increases, that's what we're saying. Basically, as x increases, as we go to the right on our graph, so as I plug in x values and I increase, I go to 1, 2, 3, 4, 5. I'm going to raise it to a power of 4 and then multiply it by 5. Those are all positive results. Plus, if you're following the leading coefficient test, the 5 is positive, and so that's kind of what determines that if you're just following that simple test. Then as far as the left end behavior, basically as my x values decrease and go to -1, -2, -3, and so on, you can focus on that power right there. And if it's an even Steven, you're going to have the same behavior as my right end behavior, which will also be positive infinity. Now, once again, just kind of maybe take a little bit of a deeper dive. Let's say that you were to plug in a negative number and raise it to the 4th power. Well, what happens is when you plug in that negative number, like -10, -11, whatever you want to pick, when you raise it to a power of 4, it actually is going to come back as a positive number and then get multiplied by 5, which is still a positive number. So anyways, this graph, like once again, there's some stuff that happens in the middle, but once it's done doing its ups and downs, it's going to go up for good to the right and up for good to the left. And that's what we're learning about right now. That's what we're trying to focus on, is this thing called the end behavior. Okay, so next we're going to talk about the x-intercepts. And so we actually already know how to find the x-intercepts, but we are going to talk about a thing, and I talked about this a couple of weeks ago, and you probably don't recall it, but I talked about a thing called multiplicity. And so in order to find the x-intercepts of a polynomial, what you have to do is set it equal to 0 and factor it and solve by using the zero factor property. Like I said, we've done that before. What's going to be new is this concept of multiplicity of your x-intercepts. And once again, this definition can be a little formal, but basically what's going to happen is your multiplicity, which we typically will use the letter K to indicate that. So if your multiplicity of your solution is odd, then it's just going to go ahead and cross the x-axis at wherever that value is. But if it's an even, if it happens an even amount of times, so what we're saying is the solution occurs more than once, then what happens is it touches the x-axis and turns around at that point. And so I have an example over here off to the side. And so if you look right here, here's my function. It's actually already factored, okay? And so one of my solutions right here is that x equals -1. And that solution only occurs, that multiplicity for that is a 1 because its exponent is a power of 1, okay? And so that means it's just going to cross through the x-axis, and you can see that right here on the graph, right there on the graph. But my other solution, which is right here, if you were to take this and set this equal to 0 and solve, that would be at x equals 3/2, or basically x equals 1.5. The thing is, that solution right here on the graph happens twice. It happens twice because really that's the same thing as saying 2x minus 3 times 2x minus 3. So that solution actually occurs twice. And so that has a multiplicity of 2. And so that's going to be one of those, sometimes we say that bounces off. You might see that terminology in your homework. It bounces off, it turns around, it touches, and so right there it just bounces off, and it almost has a parabola look to it, okay? And so what you're going to kind of see as we get more into this is depending on the multiplicity will kind of depend on how it looks when it crosses or touches the graph. And so let me see if I have a little bit of space down here. I'm going to scroll back up in a second. But typically, so if you have a function, and let's say that it's like, I don't know, we'll say x plus 2 or whatever. And so my solution to that would be x equals -2. When you graph that, typically it kind of takes on the shape of whatever that, that's a power of 1. Typically that's going to take on the shape of like a line crossing it. It's just going to kind of look like a line crossing at that point at -2. But if I have something like f of x equals, x plus 2 squared, maybe there's some other stuff there. What's going to happen is when I hit the x-axis at 2, now it could be from up above or down below, but either way, it's going to kind of come down, touch, bounce off, and then maybe come and then go back down or something like that. There might be more to it, but where that x-intercept is dependent on the multiplicity will kind of depend on how it looks when it hits the x-axis or bounces off of it. And I'm going to look at one more because we're not going to get too crazy on this, but you might get up to a power of 3. So let's say you had x plus 2 to a power of 3, and maybe there's some other stuff with the function, but we're just going to kind of focus on that. And so whenever you have a power of 3, that's odd, right? So it crosses. By the definition, it's going to cross right here, but it doesn't cross like a straight line. It actually looks like a cubic function, hence the power is a cube, right? And so it actually is going to look something kind of like this. It's going to kind of curve into it and curve out of it, and then maybe it comes up and then goes back down or something like that. Like I said, there might be more to the function. I'm just making this one up. But I'm trying to give you an idea of the 3 different types we are going to look at. We're going to look at some where it's a power of the multiplicity is a 1. If it's a multiplicity of 1, it's just going to cross right through it. It's almost going to be almost like a straight line, okay? If it's a power of 2, it's going to have that parabola look. And it could have come from underneath also, by the way. I just happened to draw it from up above, but it could go either way. It just kind of depends on each individual equation. And then we could have a power of 3, which is odd, so it is going to cross. But but it has that cubic look to it, where it kind of curves into it and curves out of it, like that we had done with our transformations. Okay, so with that said, I'm going to scroll back up and we're going to look at these graphs, and we're going to go ahead and uh, determine the zeros and their multiplicity. We're going to determine the zeros and the multiplicity of these. And so looking at this first one right here, let's see. So that x-intercept would be at x equals -2, and we typically use k to indicate multiplicity, and that multiplicity would be a 1, because if you look, it just kind of cuts like straight through it like a line. Cuts straight through it like a line. Now on example A right here, I'm sorry, yeah, on my second one right here, it looks like I have an x-intercept right here at 4. So when x equals 4, now if you look at it, it kind of curves into it and curves out of it. It's got that cubic look to it. And so that would have a multiplicity of 3 on it. That would be a multiplicity of 3. Now let's look at my example B. So this first one, I have one at x, when x is -2. When x equals -2. And once again, it looks like just a straight line going through it. So my multiplicity would just be a 1. My multiplicity would be 1. And then my other two, if you look, they both kind of have the same thing. They both have that parabola look to it. They both have that kind of that parabola look to it. And once again, you're gonna have those twists and turns in the middle. But yeah, those both. So when x equals 1, my multiplicity is going to be a 2. And then same thing with my other one. When x equals 4, my multiplicity is also a 2, because you kind of it bounces off. So remember, if it crosses, my multiplicity will be odd. If it bounces off, it would be an even power. And so we're not going to go above a multiplicity of 3, but if you were, a multiplicity of 4 looks very similar to the parabola, and a multiplicity of 5 looks kind of similar to the same as we had on our multiplicity of 3 over here. So, but anyways, the only thing you're going to have to really worry about is multiplicity of 1, 2, and 3. Okay, now we're going to get a little bit more practice, but with an equation, so not the picture. So now we got to kind of figure this out by if we're given an equation. So it says identify the key characteristics of the following polynomials. The leading coefficient term, the end behaviors, list their zeros, multiplicity, and whether they cross or touch the x-axis. Okay, so this first thing we have to do, this is something we haven't done before, but we have to figure out what the leading term is, because it's not this. It's not the -3x squared. Technically what we need to do is multiply all this stuff together, and that would actually be pretty complicated. Like, it would be very time consuming, and it would be very possible to make a mistake, right? So really what I can do here is I can kind of focus on what would get multiplied together to create the term with the highest power. And so instead of figuring out what this is right here, because to figure this out, I'd have to do x plus 2 times x plus 2 times x plus 2. That's what I'd have to do to figure out, and then I have to multiply it by the x plus, or the x minus 5, and then I have to multiply it by this over here. And so that would be very time consuming. And so what I'm going to do instead, this is a little trick. Basically, you can just apply that power to the first term, which that would be what, x cubed, right? And then multiply that by the highest power on all the other factors. So then, and then you have to include the coefficient out in front right here. So really, I mean, out of this, I'm really just kind of focused on the term with the highest power, which if you were to FOIL this and multiply it all together, the highest term would be x cubed from this. Then my highest term right here would just be an x, and then my highest term over here is -3x squared. So what I need to do is multiply all of those together, and that will give me my leading term right there. So I need to take -3x squared, multiply that by x cubed, and then multiply that by x. So if I multiply all those together, that would give me negative 3x to the power of 6. So negative 3x to the power of 6. So this is just kind of a shortcut. Instead of having to actually multiply every single thing together, what I'm trying to figure out is if I did multiply it all together, what would be the leading term? What would be the term with the highest power? So what I did was x to the power of 2, I'm sorry, x plus 2 to the power of 3, instead of having to multiply that all together, really all you have to do is apply the power to the first term right there, the term with the highest power, which that's the only term that had the variable x. So that would give me x cubed. That's what would happen if I multiplied all this together. The highest term that would come out of that would be an x cubed. Then I multiply that by the other highest, the variable with the highest power on the other factors. And so that's how I got to this right here. That's how I got to this. So really, you really don't want to overthink this. So let me kind of erase this and clean this up. So to kind of give you the simple approach to this. So really all you have to do here is if you have single terms like this, just take the whole thing. So negative 3x squared. Then if you have something like this, just wherever the variable's at, the variable with the highest power, which this is the only variable, apply this power to it, which would be an x cubed. And then here, once again, this has an understood power of 1. And so then you just take that x right there and you multiply them all together. And that's how I got this, because you add the exponents when you multiply. So x squared times x cubed times x, that's where I got the x to the power of 6. And then I had that negative 3 that was right there in front. Now, why do I care about this? Why did I even go to this much trouble? Because that's now going to help me figure out my end behavior. So now I can follow the leading coefficient test, which is if the leading term is negative, then my right end behavior is going to be negative also. So that's going to go to negative infinity. Then my left end behavior, if it's in even power, it's going to have the same result as I go to the left. So that's also going to go to negative infinity right there. So those both are going to go down. My end behaviors are both going down on that. The right end because of the negative leading coefficient term, and then also down to the left because of the even power of my leading term. All right, so that was kind of reviewing in behavior. The next part is finding your zeros. Okay, well, once again, I'm going to kind of erase some of this stuff so I can have some room so we can look at this. So here we are. So here's my first 0. That would be x equals 0. And the multiplicity is just the exponent. That's all it is. Don't overthink it. The multiplicity here is 2. And if it's an even multiplicity, if it's even, it touches. If it's odd, it crosses. So it's just going to touch and turn around or bounce off at that x intercept right there. Then my next one right here, that would be at x equals negative 2. And that multiplicity is 3, which is an odd number. And so it's going to cross. And when it does cross, it's going to kind of look like this. It's going to kind of have that cubic shape to it. Just kind of review that. When it crosses at negative 2, it's going to kind of have that shape. At 0, it's going to have a parabola shape. It could open up or down, but it's going to kind of have that bend to it, that bowl shape to it. And then my last one, my x-intercept at x equals 5 has a multiplicity of 1. It's just the exponent, which is understood as 1. So when x equals 5, we have a multiplicity of 1. If it's odd, it crosses. And that one's going to kind of be more, it's going to kind of look like a straight line going through at that x-intercept. Okay, so I have one more of these to look at, and then I'll probably stop this video and make a second one for the last part of the notes. So let's go ahead and come down here. And what's different about B is I'm going to have to factor that. But before I factor it, I want to take care of the leading coefficient stuff.
So let's see, yeah. So right here, my leading term is right there. That's just x cubed. So this one shouldn't be too bad. So as x goes to positive, as I plug in positive numbers, as I go to the right, I'm going to get positive results, right? And once again, if you follow the leading coefficient test, it's positive in front right here. It's a positive number, so my y value is going to come back positive also. Then as I go to the left, as I plug in negative numbers, since I have an odd exponent for my leading term, I'm going to have opposite results. I'm going to have opposite results. So since my right end went to positive, my left end will go to negative. Also, if you just kind of think about it, if you plug in negative numbers to a power of 3, you're going to get a negative number in return. Okay, so that's in behaviors. Now we're ready to figure out our solutions, our zeros, and then figure out their multiplicities and figure out the behavior. So in order to do that, we have to factor this. So I'm going to take this x cubed minus 6x squared plus 9x, set that equal to 0, because that's how we're going to do this in a moment. And so now we're going to factor this. So I can start by factoring out an x. So when I factor out an x, that will leave me with x squared minus 6x plus 9 equals 0. And then now I am going to factor that right there. And so you can do the A&M method if you want. So what multiplies to give me 9 but add up to negative 3? So that's going to be x minus 3 and x minus 3. Now, what you want to do is kind of clean this up a little bit, though, because if you have common factors that are the same, you can consolidate that into an x minus 3 squared equals 0. And the reason I want to do that is so that it'll make my multiplicity obvious, what the multiplicity is for that. Okay, so now looking at my zeros. Well, this first one's pretty easy. That's just going to be 0, and it has a multiplicity of 1. So one of my zeros is 0, and my multiplicity is 1, and if it's odd, it will cross the x-axis. My other multiplicity here, let's see, well, first of all, my solution, my x-intercept is 3. So when it hits the x-axis at 3, my multiplicity is a 2. So what that means is it's going to bounce off or basically touch and turn around. It's going to kind of have that parabola shape to the graph. Okay, so I'm going to go ahead and stop this video. This will be part 1, and I will make a part 2.